Hi, I'm Detective Incognito. Welcome to another investigation. I explore strange events, forgotten discoveries, and questions that still challenge what we know about our world. What you're about to hear might change the way you see everything. For 50 years, scientists called it impossible. The protein folding problem stood as biology's grand challenge, resisting every attempt at solution. Determining how proteins fold into three-dimensional shapes cost roughly $120,000 and an entire year. Per protein in 2020, artificial intelligence solved it in days, not approximately, not partially, with precision matching the width of a single atom. Subscribe now to discover how AI cracked nature's code and created an oracle that actually works. Like this video if you want to understand why this breakthrough represents one of science's greatest triumphs. Proteins are the molecular machines that make life possible. Constructed from chains of amino acids, they fold into intricate three-dimensional structures. Shape determines function. The wrong fold produces disease. Alzheimer's, Parkinson's, cystic fibrosis all result from protein misfolding. The challenge seems straightforward. Given a sequence of amino acids, predict the final folded structure. But this simplicity masks extraordinary complexity. The 1960s, Cyrus Leventhal identified a fundamental paradox. A typical protein could theoretically fold into more configurations than there are atoms in the observable universe. Random sampling through possibilities would take longer than the universe has existed. Yet nature accomplishes this folding within milliseconds. For decades, this paradox defied explanation and prediction. 1994, John Molt created CASP, the Critical Assessment of Protein Structure Prediction. This biennial competition became the Olympics of protein folding. Research teams worldwide submitted predictions for proteins whose structures hadn't yet been experimentally determined. Judges then compared predictions against laboratory results. Traditional experimental methods relied on X-ray crystallography, nuclear magnetic resonance, and cryo-electron microscopy. Each technique cost approximately $120,000 per protein and required roughly 1 year. Scientists had mapped only about 170,000 proteins. For millions that exist, this bottleneck strangled drug discovery. In disease research, computational predictions might offer shortcuts, but decades of attempts yielded minimal success. The problem seemed fundamentally unsolvable, requiring understanding of quantum mechanics, thermodynamics, and biochemistry simultaneously. In 2018, CASP-13 convened in Cancun, Mexico. Among established computational biology labs appeared a newcomer, DeepMind. The artificial intelligence company that had conquered Go and StarCraft, brought AlphaFold to its first protein folding competition. Demis Hassabis, DeepMind's CEO, had described games as stepping stones toward applying AI to fundamental scientific problems. AlphaFold represented that vision realized. The results stunned the community. Researchers walked around in a daze. According to multiple accounts, AlphaFold didn't simply win. It put what one scientist called significant sunlight between itself and all competitors. While AlphaFold still couldn't match laboratory accuracy, it had left traditional computational methods in the dust. John Molt, CASP's director, noted that the community took serious notice. By CASP-14 2 years later, over half the entries employed deep learning. Many explicitly adapted their approaches to work more like AlphaFold. David Baker at the University of Washington created Trozeta, inspired by AlphaFold's methodology. It became one of the strongest traditional competitors. Yet it still came what Baker called a very distant second to what DeepMind would unveil next. Between competitions, expectations centered on incremental improvement. The reality brewing at DeepMind proved far more revolutionary. On November 30th, 2020, DeepMind made an announcement that would reshape biology. John Jumper presented AlphaFold 2 results via Zoom. to a scientific community still working remotely during the pandemic. The CASP-14 competition had concluded weeks earlier. DeepMind's scores were unprecedented. AlphaFold 2 achieved a median GDT score of 92.4, over 90% accuracy, across the protein set, 5 times better than the nearest competitor. The margin of error measured 1.6 angstroms, roughly 0.16 nanometers, the width of a single atom. For the first time, a computational method matched laboratory experimental techniques. In accuracy, John Molt declared the 50-year grand challenge largely solved. Mohammed Al-Quraishi at Columbia described being in shock. Many colleagues were in denial. Venki Ramakrishnan, a Nobel laureate in chemistry, called it a stunning advance on a long-standing problem. Janet Thornton at the European Molecular Biology Laboratory validated the predictions against experimental structures. They held up. The system operated in days rather than years. At a fraction of traditional costs, AlphaFold 2 employed transformer architecture, the same foundation underlying modern language models. It analyzed multiple sequence alignments, combined with evolutionary data. An attention-based neural network processed this information, trained end-to-end on known protein structures. The system refined predictions through iterative processes, essentially teaching itself the physics of protein folding. When applied to ORF8 from SARS-CoV-2, AlphaFold produced accurate structure predictions in roughly 30 minutes. What would have taken a year in a laboratory happened during lunch. In July 2022, DeepMind partnered with the European Molecular Biology Laboratory to release something unprecedented: 200 million protein structure predictions. Essentially every cataloged protein known to science. The entire protein universe mapped and made freely available to researchers globally. Millions of scientists now use AlphaFold in their work. Applications span malaria vaccine development, cancer treatment research, and enzyme design for industrial processes. The scientific literature contains over 20,000 citations to AlphaFold. The work earned the Breakthrough Prize in Life Sciences. 2024, DeepMind announced AlphaFold 3, extending beyond proteins to DNA, RNA, ligands, and ions. The new system predicts how these molecules interact, achieving 50% improvement over existing methods. AlphaFold Server launched, offering free access for non-commercial research. Isomorphic Labs, DeepMind's sister company, applies these methods to pharmaceutical drug discovery. Major collaborations with drug companies have begun. CASP-15 occurred in the post-AlphaFold era. DeepMind didn't participate directly, yet all winning teams employed AlphaFold-derived algorithms. DeepMind had, in a sense, invisibly won again. By transforming how everyone else approached the problem, the digital oracle they created actually works. AlphaFold succeeded where other prediction systems failed, because it didn't merely find correlations. It learned actual patterns grounded in physical reality. The system combined evolutionary history with physics constraints and structured data. Unlike failed oracles such as Google Flu Trends, which confused correlation with causation, AlphaFold engaged with genuine biological mechanisms. Scientists still debate whether the AI truly understands protein folding, or simply pattern matches with extraordinary sophistication. John Jumper described it as machine learning meeting the complexity of protein machines. The crucial insight is that some problems are solvable when enough data combines with appropriate architecture, but only when the underlying problem has genuine regularity. Protein folding is governed by physics, by thermodynamics and quantum mechanics. These follow consistent laws. They don't change based on news cycles or algorithm updates. AI oracles work when predicting natural law, rather than arbitrary human behavior. This represents a template for AI in science. The methodology applies to other grand challenges, in structural biology and beyond. AlphaFold demonstrates that prediction becomes possible when grounded in understanding rather than mere statistical association. The next frontiers include RNA structures and protein complexes where multiple molecules interact. The digital oracle succeeded not by seeing an unknowable future, but by learning nature's language. In a universe governed by physical law, prediction becomes possible. When you comprehend the rules, AlphaFold didn't break nature's code. It read what was already written. In the laws of chemistry and physics, sometimes the oracle works. But only when asking questions, nature knows how to answer. Only when prediction and understanding become the same thing. If you liked what you just saw, like the video, subscribe to the channel, and activate the bell. Leave your opinion in the comments below to let me know what you thought. Thanks for sticking around, and see you in the next video.